Students, today we'll discuss the performance evaluation of the transformer. There are two things we have to discuss here. One is the efficiency of the transformer, then the voltage regulation of the transformer. We'll start with the transformer efficiency. Before that, how the transformer is rating. I told you in the last class that transformer is rated in terms of its volt ampere. That is, they are not rated in watts. The load power factor is unknown. We know that in the case of a transformer, at a particular voltage, you are delivering the load current, transferring the electrical energy from primary to secondary. That is, we are having a secondary winding here, then you are connecting a load here. The current which is delivered to the secondary because of application of the voltage V1 and the current input as I1. Here, the what type of load you are connecting we don't know, but we know, however, what is the rated voltage, terminal voltage V2. We know the V2 I2 in the output side. At the same time, we know what is the input to the transformer in terms of V1 and I1. Based on the type of the load, for example, if it is a cos phi is the 0.8, then the output, we know that the power equation is, what is the power equation? It is a product of voltage, current and power factor. In that case, if you know V2 I2 and we know the load power factor, then the output as it is V2 I2, the cos phi it is in terms of watts. That is why they are telling the transformer rating, they are not rated in watts. The load power factor is unknown. If the power factor is changed from 0.8 to 0.7, then the output of the transformer will change because V2 I2 remains same. Because of the power factor, the output will change. Therefore, the power is equal to, it is volt ampere multiplied by the power factor. That we are discussed in the. Then we'll define what we mean by the efficiency. What is the efficiency? The efficiency is in general and is the ratio of the output to the input. That is, the efficiency is defined as it is output by input. Okay. Now, if there are some losses in the machine, in that case, we are modifying this efficiency equation. That is, can express the efficiency in terms of output and losses or input and losses. If you know any one and the losses, then you can express efficiency as, I will express the efficiency in terms of output and the losses. That is, output is known V2 I2 cos phi, output. Then how we are expressing input? It is, input is output plus losses. Output plus the losses. Similarly, in the same lines, how we are expressing your efficiency in terms of input. The output is nothing but, it is the input minus losses. Input minus losses divided by the input. This is how we have to express the efficiency. Either efficiency is output by input, or it is output by output plus losses, or input minus losses divided by input. Usually the efficiency is expressed in terms of percentage. Therefore, it is output by input into 100. Then it is called as percentage the efficiency. The same thing is discussed here. It is a ratio between the input power and the output power. That is, efficiency is output power divided by input. We know that the input is the output plus the losses, output plus losses. Therefore, the efficiency can be written as it is the input power minus losses divided by input. That what we are expressed here. Similarly, we can express in terms of output, that is output power divided by output power plus the losses. This is how we have to express the efficiency. It is in general, it is the output power to the input power. Then the efficiency is normally expressed, I told you, as in percentage. Therefore, it is output power by input power into 100. In graphic that in pictorially we are shown here, there is a power input to the machine and power output to the machine. In between here in the transformer you have got the two losses. One is called as the iron loss, then the another one is called as the copper loss. That is, if the ideal transformer power input is equal to power output, because of the losses the power output is not equal to the power input because of the losses inside the machine. In the case of the transformer, we have got two losses. One is called as iron loss, the another one is called as the copper loss. Because of that, the output is less than the input. The transformer losses. The first one I told you there are two types of losses. One is called as the iron loss, the another one is the copper loss. The copper loss, it is varies with the load current, produces heat created by resistance of the winding. The copper loss, the total copper loss, it is expressed as I1 square R1 plus I2 square R2 watts, or if you are expressing the equivalent resistances, refer to the primary and the secondary. It is I1 square RO1 is equal to I2 square RO2. We will elaborate thus the copper loss. That is, the copper loss is nothing but it is a I square loss or loss. The copper loss is it is basically I square R loss. Wherever there is a resistance, in that there is a power loss, that is it is called as I square R loss. It is I square R loss. It is I square R loss. We know that it is the transformer made up of two winding. It has got its own resistance. Therefore, the transformer is represented with the resistance. If you are representing resistance, also it has got its own leakage reactance. It also has got leakage reactance. Okay, this is a primary winding. Then in the secondary also we have got the resistance and inductive reactance. Then you are connecting here the input, that is V1, the current which is flowing in the primary is I1, the current delivered is I2. If you are connecting a load here, it's a load here, then the voltage is the V2 here. Then we have got it is R1, the X1, it is R2 and X2, where the R1 and R2 are the resistance of the primary winding and secondary winding. R1 and R2 are resistances of primary and secondary windings. Whenever there is a current is flowing through a resistance, therefore there is a loss occurs, that is primary copper loss. How we are getting? That is the current flowing through the primary resistance, that is I1 square R1, and similarly secondary copper loss is I2 square R2. It is so many watts. Then what is the total copper loss? The total copper loss is equal to sum of these two losses, I1 square R1 plus I2 square R2. It is so many watts. This is a total copper loss. Then if you look into the copper loss, it is depending upon I1 and I2. If the load increases, the current I2 increases. If the I2 increases, current drawn from the supply is also increasing. As the load changes, the I2 changes. In turn, the I1 is also changes. When there is a current is change, then the copper loss is also changed. Therefore, this loss is called as the variable loss. It is called as a variable loss because the copper loss is depending upon the load current. That is why he is telling that it is varies with load current. Whenever there is a loss occurs, it producing a heat. I told you it is created by resistance, that is I1 square R1 plus I2 square R2 is the total copper loss. Suppose if the resistance is transferred to the either primary side or the secondary side, then it is called as equivalent resistance. That is, I told you it is RO1 is equivalent resistance of the transformer referred to the primary side. Means R2 is brought to the primary side, then they are finding out the total resistance. That is, RO1 is it is the sum of R1 plus R2 referred to primary. Primary means the total resistance is transferred to the primary. That is what we are calling RO1. Similarly, if we are transferring this resistance to the secondary side, in that case it is R2 plus R1 referred to the secondary. Then in that case, if it is RO1 is taken the total resistance, in that case the copper loss is it is I1 square RO1, or it is, if you are referring to the secondary, it is I2 square RO2, so many the facts. This is how we are calculating the losses for the primary and the secondary, refer to the primary and secondary. Means in general the copper loss is the variable loss. It is varying with the load current, then it producing a heat. The next one is the core loss. The next one is what we are calling is the core loss. It is also called as iron loss, or it is also called as core loss, also called as constant loss or a constant loss. Okay, basically the two type of losses. One is the variable loss, that is the copper loss. The another one is constant loss, that is called as iron loss or a core loss. Here the iron loss is consist of two component. One is called as hysteresis loss and another one is the eddy current loss. These losses are fixed loss, whereas the copper loss is the variable with respect to load, it is changing. However, the iron loss remains the constant. Irrespective of the load, the iron loss is present. Whether the load is connected or it is under no load condition, the iron loss is always present in the transformer. It is related to transformer construction. It is relevant to the related to transformer construction. Okay, the first we will discuss what we mean by hysteresis loss. The hysteresis loss is that energy lost by reversing the magnetic field in the core as the magnetizing AC rises and falls and reverse direction. I will elaborate on this one. We will see the salient features of the hysteresis loss. Hysteresis loss depends upon the following: the area of the hysteresis loop. In turn, it is nothing but it is directly proportional to the flux density. Then it is a volume of the core. Then the frequency of the magnetic flux reversal. On these three factors, the hysteresis loss depends. That is, in turn, the iron loss has two components. One is hysteresis loss. The another one is eddy current loss. Combination of these two is constituting the iron loss, eddy current loss, eddy current loss. Then what he is telling you here is hysteresis loss is that energy lost by reversing the magnetic field. We know that all the magnetic materials are made up of a small teeny particles called as the dipoles. For example, it is NP, 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 NP. So many small particles they are consist of. Then when if you are wound the winding on this, that is you are wound the winding on this magnetic core, then you are connecting here the AC voltage. You are connecting AC voltage. Then what is the nature of the current here? It is also in AC in the nature. That is, when this is positive with respect to negative, a positive half cycle, then all these magnetic dipoles, they are arranged in a systematic manner, that is N and S, N and S, N and S, like this. When this is positive, then this is a negative. When next half cycle, this has become a negative, this will become a positive. In that case, suddenly what happens? These dipoles, they are changing their direction. They are changing their direction. Then it is become N, S, N, S, N and S. Next half cycle, once again it is become positive, this has become negative. Once again they are changing the direction. Then when there is a change in the supply here from positive to negative, negative to positive, means first half cycle and the negative half cycle, they are changing their direction. When they are changing their direction, they are brushing each other. That is, there is a friction between the dipoles. Because of this friction of the dipoles, there is a loss is occurring. That loss is called as hysteresis loss. That is called as hysteresis loss. Therefore, he is telling that hysteresis loss is that energy lost by reversing the magnetic field. Then the friction between the dipoles is depending upon what? It is depending upon the flux density. If the magnetic material, very good quality magnetic materials, it contains more number of dipoles. If there are more number of dipoles, because of the reversal of the supply here, then more number of dipoles are come into there is a brush between the dipoles are more, or brushing between the dipoles are more. Because of that, the losses are more in that is hysteresis loss is more. If the flux density is more, means more number of dipoles are there, therefore there is more hysteresis loss. Then the volume of the core. If the core of the magnetic material is more, there are more number of the dipoles. If the more number of dipoles and the brushing between the dipoles is more, because the volume of the core itself is more, therefore hysteresis loss is also more. And it is also depending upon the frequency of the magnetic flux reversal. What do you mean by that? If the reversal takes place very fast, then the changeover from N to S, S to N is the frequency is more. Because of more friction between the dipoles, then there is a more loss. Therefore, the hysteresis loss of the iron loss is depending upon, it is the area of hysteresis loop, or it is a flux density or volume of the core, as well as the frequency. There is an empirical formula for hysteresis loss that is depending upon, that is eta, that is the hysteresis constant of the particular material. It is depending upon the quality of the magnetic material, that is it is varying from 1.6 to 2.1, and it is V. V is not a voltage here, it is a V is volume of the magnetic frame, and the F is the frequency, that is eta, V and F. And it is also depending, I told you, it is depending upon the magnetic flux density. It is also directly proportional to the volume. It is also proportional to the frequency. Therefore, the hysteresis loss is given by an empirical formula, that is E eta V F B max is to eta so many watts, where V is the volume, F is the frequency. This is how they are calculating the hysteresis loss. Then how you have to reduce this hysteresis loss? To reduce the hysteresis loss, say special steel in the laminations, it has to be made up of a laminations, and it is also made up of good magnetic material. It is usually they are using cold rolled grain oriented, or it is, in short, it is called as CRGO. CRGO, the magnetic material they are using for to reduce the hysteresis loss of a transformer. Then the another loss is what we are calling is the eddy current loss. Another one is called as eddy current loss. The eddy current loss is a result of induced current circulating in the core. I will elaborate this one. First we will see that the eddy current loss depends upon the following factors. Thickness of the laminations of the magnetic core and yoke, that is a T, the frequency of the flux reversal F, the maximum value of the flux density in the core, that is Bmax, and it is also proportional to the volume of the core or yoke, that is V, and the quality of the magnetic material used for the magnetic frame, that is, it is represented with a constant K. What do you mean by the eddy current loss? The eddy current loss is nothing but, I'll elaborate this with the help of this diagram. Yes. Okay. This is the magnetic core. I told you this is made up of laminations. It is not a solid magnetic core. It is made up of laminations. Okay. What is our objective? Our objective is to transfer the electrical energy from primary to secondary without any electrical connection. Then whatever power you are inputting, that maximum output, it should be transferred to the secondary side. Then what happens? Whenever there is an alternating current is flowing here, then alternating flux is producing, which is linking both primary and secondary winding. Then because of the flux is changing with respect to time, there is an induced voltage in the primary winding and secondary winding. At the same time, you have to look into you forget about the primary and secondary windings, you have got a core. The core is also subjected to change of magnetic flux. The flux is linking through a magnetic core. The magnetic core is made up of laminations, that is very small laminations. They are separated by the insulation. Then when the flux linking with the laminated core is changing, there is an induced voltage in the magnetic core also. That is, because of this change of flux, it is also this magnetic material is also conducting material. Therefore, there is an induced voltage in the magnetic core, laminated core. Then because of the induced voltage in the magnetic core, there is small current is flowing in the magnetic core. That current is called as eddy current loss. The magnetic core has got some resistances, therefore eddy currents are flowing, therefore there is a loss in the magnetic core. Then how to reduce that one? If you are making a solid body, the cross-sectional area of the magnetic core is more. Therefore, R is equal to rho L by A. Rho L by A. If it is reduced, if the cross-sectional area is reduced, that is, you are making a laminations, so that you can reducing the losses, that is, whatever the currents they are inducing in the magnetic core. That is, it is highlighting here in the hysteresis loss, eddy current loss. That is, eddy current loss is result of induced current in the current circulating in the core. The current which is flowing in the magnetic core, they are causing a losses. That loss is called as eddy current loss. The eddy current loss depends upon, once again, it is a thickness. It is depending upon the thickness of the magnetic core, that is a lamination. It is also depending upon the frequency of the flux, that is F. Also it is depending upon the maximum flux density. If there is a more density, there is more eddy current, EMF is inducing, thereby there is eddy current is also increasing. It is also depending upon the value of the core and the constant. Then the empirical formula for that, the eddy current loss, is expressed as it is kV B max square F square T square fats. That is, the eddy current loss is proportional to the volume of the magnetic core, the maximum flux density in the magnetic core, the frequency of the applied voltage, and also it is the thickness of the magnetic core. These are the losses that is causing because of the iron losses. These are the constant losses. It is how to reduce this. It is reduced by laminations. It is also producing a heat. To minimize the eddy current loss, we use the iron core, which is made up of laminated stampings. The thickness of the stampings here is around the 0.5 mm. This is how we are using a laminated core so that you can minimize the eddy current, the loss. Then if you are observing the formula for hysteresis loss and the eddy current loss, it is depending upon the volume. The volume of the magnetic core remains same. It is not changing. Once the machine is designed or the transformer is designed, the volume remains same, thickness remains the same. Then the flux density in the magnetic core is depending upon the constant applied voltage. If the voltage is more, it is producing the one particular value of the magnetic flux in the magnetic core. That is also constant. Then the applied voltage frequency is also constant. Therefore, the volume of the magnetic core is constant. The maximum flux density which is producing the magnetic core is also constant. The applied voltage to the frequency of the applied voltage to the transformer frequency is also constant. The T is also constant. Then it is not depending upon the load. Therefore, irrespective of the load, the eddy current loss is also constant. At the same time, the hysteresis loss also, it is depending upon the volume, frequency, maximum flux density. Once again, the volume of the magnetic core is constant, the frequency is also constant, applied voltage frequency is constant, and the flux density is also constant. Therefore, hysteresis loss is also constant. Then the combination of the hysteresis and eddy current loss put together is a constant. Therefore, it is called as the constant loss. Also, it is occurring in the core. Therefore, it is called as the core loss. Also, it is called as the iron loss. Basically, in the transformer, we have got two losses broadly, transformer losses. That is, one is the variable loss. That is what you are calling is the copper loss. It is depending upon the load. Whereas another one is the constant loss. It is nothing but it is called as iron loss, or it is also called as the core loss. In the next class, we'll see how the efficiency is calculated, then the condition for efficiency, and some of the numericals on the efficiency.